We're going to look at big topics 1 and 2 as a review. That's atoms, elements, structure, and properties of matter. And away we go. So first problem. And this one's actually from 2013, so this is one of the oldest ones we have. So right away, it lays it out for you using principles of molecular structure and intermolecular forces. So they give you two compounds, they give you the formulas, they say if they're soluble in water, and they give you some boiling points. All right. So compounds 1 and 2 in the data table above have the same empirical formula, but they have different physical properties. Quickly, empirical formula means the simplest whole number ratio. So I have a feeling that although that's the formula, it's probably not how the atoms are orchestrated around each other. At least they're not going to be exactly the same in their bonds. So A, the skeletal structure for one of the two compounds is shown below in box X. I, complete the Lewis electron dot diagram of the molecule in box X. Include any lone non-bonding pairs of electrons. This is about as much hand-holding as they're going to ever do for you, right? I mean, they've already literally laid it out here. So include any lone non-bonding pairs of electrons, but then hopefully you're assuming I'm probably including bonds themselves, right? So we're going to bond that. I'm trying, that's not matching up very well. There we go. I'm going to bond the O to the H. And then what's the last thing I need to do? I'm not going to ask a lot of questions, but hopefully you can help me with this one. What do I need? Yeah, just two lone pairs, right? Like that. Okay, then we scroll down, and it says in box Y above, draw the complete Lewis electron dot diagram for the other compound, which is a structural isomer. This is why we did our organic unit, which is above and beyond AP chemistry, of the compound represented in box X. Include any lone non-bonding pairs of electrons. So you got to come up with some other idea. All right. So what do we know? The one element that is always part of the chain is carbon, right? What else do we know? We always know that the hydrogens are on the outside. So basically it comes down to the O. So does anybody have a thought? I mean, if you don't, that's okay, but there's a couple that we learned about. I mean, how could I rearrange that? It's the chain that I have to rearrange, most likely. That's what I'm going to go at. So I kind of wrote a carbon here, and I think about what's in the middle. All right. Well, maybe I just rearrange the order a little bit. So what if I did something like this? Honestly, you're going to know if you're right if you still have the same number of bonds and the same number of lone pairs. So I have 6 H's. Let's see if that works. Okay. And then what does the oxygen get? 2 lone pairs. And that does work. Okay, that is an ether. We learned about that. It's not asking you for the name, but that's an ether. And you get a point for that. So those are the two different ones. That, obviously, of the two parts, much more difficult, if you're recognizing that or not, and they didn't give you a lot of clues to go off of. Letter B says, on the basis of the complete Lewis electron dot diagrams you drew in part A and the information in the data table above, identify which compound, 1 or 2, has a structural represented, or has a structure, I'm sorry, represented in box X. Justify your answer in terms of intermolecular forces. So let's talk about that. Which compound is X? So we got compound 1 and compound 2. So really, there's two things going on here. It says that compound 1 is slightly soluble in water. Compound 2 is soluble. And then it says that this is a much lower boiling point for compound 1 than compound 2. So IMFs, if we remember about IMFs, I'll go to B here. IMFs, we are talking about a couple things here. We're talking about LDs. We're talking about dipole-dipoles. And we're talking about hydrogen bonding. Okay? And if you remember, this is about being nonpolar. This is about being polar. That's a big deal. Right? That's what it's all about. So, what do we know? Water is polar. So, like dissolves like, we say, because you have interactions with each other. Charges are attracted to other charges. So, what you need to do is figure out which one is probably more attracted to the water. So, number 2 looks like it's much more soluble. the number 1 says it, so that means this is much more polar. This one's more polar. This one's less polar. I'm not going to say non-polar, but it's less polar, so the polarity is greater on here. So between the two, how do you figure that out? Well, you could eye it up by just saying symmetry. So if it's more symmetrical, it's more non-polar, right? If it's asymmetrical, it's more polar. So between the two, X looks much more asymmetrical, right? It's uneven. Boiling point, last thing to kind of talk about here, the higher the boiling point, that means the more energy it takes to overcome the attractive forces to become a gas. So this looks like it has a stronger, and I would actually just write this on the top there somewhere. This one has a stronger IMF. Remember we talked about it, every single thing you can test, boiling point, melting point, surface tension. The bigger it is, the stronger the IMF, except for one, vapor pressure. It was the opposite. It's the only one. So, how can I talk about it? What's going on in this one? Right here, that's an H bond. This one overall, you might have a little bit of dipole-dipole, but because it's really even in box Y, that's actually very much, you got a lot of LDs going on in there because it's very symmetrical. So, I forgot the question. Which one's box X? I would say it's compound 2, right? Let me say that. And it actually says this. Compound 2 is in box X. Would have intermolecular hydrogen bonding, which is a stronger dipole-dipole, while the other one only has dipole-dipole in London. So if you were going to break this down, that's hydrogen bonding. There's a lot of LDs here. Maybe a little dipole going on because of this area. Okay, so 2 points. 2 points are in for the identification of the compound 2 and a rationale that references the types of IMFs. Okay, so again, the more soluble it is in water, the stronger the IMFs. So you got to look, does it have H bonding? Is it polar? Is it asymmetrical? Those are things that go towards that. So making little extra notes, and I hand selected these problems as the newer problems to really kind of be our final examples to help us with that. All right, moving on. This is a big problem. We have a little bit more to do. For letter C, they give you a bunch of stuff again, some loose electron dot diagrams. They give you some boiling points, and they give you some vapor pressure. Hey, we just talked about vapor pressure a second ago. It says dichloromethane has a greater solubility in water than carbon tetrachloride. So it already, oh, it didn't tell us that yet. Greater solubility. So this one has a greater solubility than this one. That's what it just said. Account for this observation in terms of intermolecular forces between each of the solutes and water. So again, you got to look at that. Well, what's the difference? This is completely, the bottom one, carbon tetrachloride, is completely symmetrical, right? The more symmetrical it is, the more nonpolar it is. So then you'd only have LDs. So what I would say is, I'm going to label it literally right here on the side. So letter C is that here, if it's polar, minimum, I have dipole-dipoles going on. Versus London forces. Okay, so, and then you do need to explain that a little bit. Just remember, water is polar. So to have a polar compound, you need to have charges, or you need to have end. A dipole is basically a molecule that has a positive and a negative end. So the attractive forces that are dealing with the dipole will be attracted to the water. If you're ever worried about how do I talk about it with the water, is that this will cause an attraction with the water molecules, or attractive force. Okay. Well, London forces, there's no charge there. So no charge with London versus the highly charged hydrogen bonds of water, there's not going to be much interaction. Okay? So the more polar something is, the more interaction it's going to have with my water. I will read what it has. It says CH2Cl2 is polar, whereas CCl4 is not. Therefore, CH2Cl2 interacts with water via dipole-dipole forces, while the CCl4 only interacts with water via dipole-induced dipole forces, or London, which would be weaker. As a result, CH2Cl2 has a greater solubility. So that's why it has a greater attractive force. So it can dissolve and interact. That's a key word. It interacts with the water, or there's an attraction with the water molecules. Letter D, in terms of intermolecular forces, explain why dichloromethane has a higher vapor pressure than carbon tetrachloride. Okay, let's quick talk about that. That is something students mess up a lot on. Vapor pressure is the ability for it, for lack of a better term, for the liquid to evaporate quickly. So if you're going to evaporate quickly, that means the greater this is, the less attractive forces. Okay? Because they're escaping. They're not attracted to each other, so they're like, see ya, I don't need to stay a liquid any longer, I'm going to become a gas. Gases have less attraction. There's less attractive forces going on in between gas particles than liquid. So if it can evaporate really fast, that means it has very low or weak IMFs. So vapor pressure is the only one that the greater the vapor pressure, the weaker the IMF. It's the only one. So how would I say that then? Well, it says that the dichloromethane has a higher, okay, so now you come up here, I was ready to go with this. You come up here and it's contradicting the information, and this happens. It's nice, you didn't have to have this memorized. So you go up here and go, oh, wait, that has lower IMFs, that should have been a higher vapor pressure, and the top one has a stronger IMF, so it should be stickier, so it can't leave as easily. This should be the weaker vapor pressure. So now what you have to do is take a breath and go, how do I make sense of this? Because clearly, what has to happen is that you have to understand that for some reason, these are sticking to each other more. So for some reason, in this case right here, you have a stronger IMF in this box. I'd actually write it in this box. You have to make sense of this. It's not an accident. I approach this exactly the way I wanted to approach this, and then I get up there and go, wait, whoops, it's contradicting. Okay, take a breath, make it make sense. So, what do I have to think about? What is the one thing with LDs? How do they become strong? The strongest LDs are bigger or smaller molecules. They are bigger, larger electron clouds. If I want a strong London force, I would have large electron clouds. I know this is starting to get a little jumbled. This one's a complicated multi-step problem. So if you look at this, see how you have two more chlorines in there, and here you have two little H's. Okay, so what you have to rationalize then is that the large electron clouds apparently have made a stronger London force than the dipole-dipole that exists in the other one. It's the only way. And you're like, but that doesn't make any sense. But I'm using the numbers that are telling me that. Okay? So this one has a higher vapor pressure, meaning that these must have weaker IMFs. So these clouds, they are bigger. Chlorine's much bigger than hydrogen. Much bigger. So they must have a larger London force. Let me read what it says here, because that was kind of crazy. Because CH2Cl2 has a higher vapor pressure, the combination of the London and the dipole forces must be weaker than the strong London forces in the CCl4. Actually, I'm surprised that they did not go further. The reason why, the Cl's must be bigger, or they are bigger, causing the Londons to be stronger. So just understand, you just take a breath and go, okay, wait, well, those London forces must be stronger than those dipole-dipoles. So 2 points are earned. 1 point for referencing the type of IMFs on each of the compounds. So you just have to say what was going on in each, which is funny because we said that in the last one. Just had to say it again. A little weird. Almost done. So once in a while, you're going to be given. What I like about AP tests, though, in that fact, is that they do tell you the situation. Now you just need to say, okay, I need to take my knowledge and make it make sense. Usually it doesn't contradict logic. That one did. Last part. probably the biggest problem. The complete Lewis electron dot diagram of methanol is shown in the box below. Molecules of methanol can form hydrogen bonds with water. In the box below, draw a water molecule in a correct orientation to illustrate a hydrogen bond between a molecule of water and the molecule of methanol. Use a dashed line to represent the hydrogen bond. Okay, so I'm amazed how many students will get this wrong. First, let's just talk about water. You didn't have to do it necessarily like this, but if you see the rest of it drawn kind of like it's having angles, then you probably should draw water the way it should be. So you should know water's bent. There's certain molecules we should just know more of. So what is a hydrogen bond? Hydrogen bond happens between what? Well, you have FON with hydrogen, right? So it's either with F, it's with O, or it's with N. So if I bring this over here, what's the hydrogen bond going to be? You probably have more than one choice here, but I kind of focus on that O right there. It doesn't tell me where to start it. So I need to orchestrate that and orientate that just correctly. It doesn't matter how I have it. Maybe I have it like this. And then, that's an example of a hydrogen bond. It's between the O on one compound to the H on the other. That's my H bond. Okay, and it's an attractive force, and that's how it dissolves things. That's how, when we talk about dissolving, it's being attracted to the water in that nature, and you just get a point for that. I believe if you did the oxygen or one of the H's, it would have been a similar answer. Okay, so that was big. That was a lot of points. All right, let's change gears a little bit. And this one's from 2015, so only 3 tests ago. They give you a list of compounds and melting points. This one's a lot shorter, so you can imagine it's probably, that first one we did was probably a question 1, 2, or 3, and that was probably worth about 10 points. This one's only going to be worth 4 points. So a student learns that ionic compounds have significant covalent character when a cation has a polarizing effect on a large anion. As a result, the student hypothesizes, so they don't know, they're coming up with a theory, that salts composed of small cations and large anions should have relatively low melting points. That's what they're saying. So if I have small cations, large anions, I have lower melting points. A, select 2 compounds from the table that explain how the data supports the student's hypothesis. Okay, so all this is honestly seeing is that if you understand a couple things. One, if you know what the heck cation and anion is, and then you're able to actually understand which ones are small and which ones are large. That's really what this is all about, okay? So if you understand atomic radius on a periodic table, right? As we look at a periodic table, right, it gets bigger, it increases going down to the lower right, right? We talked about it kind of like a snowman. So it gets bigger as it goes down, it gets smaller as it goes across. So you just have to find any 2 to kind of talk about this, but not, well, sorry, I shouldn't say any 2. You need ones that have a small cation and a large anion have lower melting points versus something that doesn't have that. So can you have a few different choices to do that with? But to me, if you notice, the first 2 have the same anion, by the way, it's the second one, iodine. And then the next 2 have the same anion. So if I look, F is about the smallest atom and ion there is. F's way up here. So to me, that is not a large anion. So to talk about this correctly, you probably don't want to focus on the F. So the best debate probably, I mean, there's you could do one here, but I would talk about it in terms of Li, Lii, sounds weird, versus Ki. Okay, that's what you want to talk about. And again, there are some other ones you could address, but this one probably does this the best. So if you talk about Li versus Ki, Lii has a small cation and a large anion. This is very small. This is very large. Okay, and then you go to the next one, which this is bigger, and this is the same, so actually I don't even need to talk about it. This is larger than that. So if you look at it, well, there I go. I have 449 versus 686. The whole hypothesis was if I have a small cation and a large anion, I have a lower melting point. That's what it's basically saying. I mean, you could, honestly, you could look at these two. Although F is not very big, Li is smaller than Na. So the fact that Li is smaller, hey, I got a lower melting point. So that also confirms it. You could have picked that one too. So all you had to say was, well, Li is smaller than K. You have to use words, and it has a lower melting point. And you're proving it right there. Okay. So that's how that one would work. And if you're like, well, what if I did an Li versus a Ki? Technically, that would work, but it's a little trickier, or LIF to LII, because F is not as large. It's smaller, so that's why you have a larger melting point. The larger the anion, the smaller the melting point. So you could also went in that direction. So you could have done this as well. There's a lot of them that you could have done. It depends on where your brain went. So if you're trying to prove, well, the smaller it gets on the front end, I get a lower melting point. Or the larger it gets on the back end, the lower melting point I have. So that was 2 points. 1 point for picking a proper debate. So these are some of the brackets that I'm picking up. And then 1 point for a correct hypothesis. Letter B, this one's interesting. Identify a compound from the table that can be dissolved in water to produce a basic solution. Write the net ionic equation for the reaction that occurs to cause the solution to be basic. Whew, okay. So, what has to be present for it to be basic? OH minus. So if you're stuck, this is what I would do. If I'm ever stuck, all of these are salts. This was probably the hardest part of this chapter when we did this. We did equilibrium, and I asked you to find the pH of a salt solution, and we had like multiple steps, and you had a hard time picking out what ion you had to write. It was hard. So this is what I suggested for people. If you take water, and you know it's going to be acidic or basic, you place that here. So, this is the trick. These are all salts, all of them. So, I'm trying not to pick one that's an actual answer. So, like for this, for example, Ki, it's going to break apart into K and I. This is going to break up into Li and I minus. They're all going to break up into ions. And those ions are going to react. And depending on which one you pick, you're going to make the salt. So, let's talk about what's happening here. What do I have over here? Well, if this created OH, that means I have an H sitting here yet. Right, don't I? Like, just tracking it. What do H pluses have to attach to? They have to attach to negative ions. Right? They have to attach to a negative ion. So you have to figure out which one of these makes sense. Which one would make sense to that? So a lot of times, if you're not recognizing this, you want to try to maybe make a weak, if you're making a base, then that means that this base would be an acid, so this could be a conjugate acid, so like a weak acid. So what is stemming from a weak acid? Well, there are a couple of them, but I'll tell you now, F is one of them. You could have picked F, so either one of these would have been awesome, because both of these have an F minus coming off of it. And I feel like, well, why can't I do the other one? Can anybody tell me why I can't have that? What is HI versus HF? Yeah. This is why this problem's actually hard. You didn't get an option. You had to pick one of the two F's. Some of you are staring at me like death is just happening. HI is a strong acid. That's not going to be basic. That's going to be, if you made if this would even work, and you have a OH minus here and then HI sitting on the right side, you're going to have that battle, and potentially that's just going to neutralize itself. So you have to have a weak acid on that side. So that actually is why, just so you understand, why it would have been bad. So you might have gotten lucky. But this is how you would have started that one off. So actually, of the two parts, that is tricky. I would have started off in the red, and then you realize, well, the conjugate partner needs to be a weak acid for that to work. So salts are tricky. Salts are really tricky. You definitely try to go over that a little bit more as we go. Okay. All right, let's change gears again. And there's only so much in big ideas 1 and 2, but I want to try to cover different kinds of problems that we're going to run into. So here, this one's interesting. We get a bunch of nonmetals, and then it says a formula, and then if you notice it, it has all these things with F's. And it says some binary compounds that form between fluorine and various nonmetals are listed in the table above. A student examines the data in the table and poses the following hypothesis. The numbers of F atoms that will bond to a nonmetal is always equal to 8 minus the number of valence electrons in the nonmetal. What? Okay, so when I read this, I needed to figure out what it was saying. Okay, so this is what I did. Is I took like 2 of these and I just said, okay, so it's about the S. So S, like in this one. So S has 6 valence electrons. It's right on the periodic table, right? Group 6A. So it said 8 minus the number of valence electrons equals the number of fluorines. So, oh, there's 2. Okay, I need to do 1 more. So that's S. Let's do carbon. So carbon, 8 minus, oh, that has 4 valence electrons. That equals 4. So that should be CF4. It is. So that's what it's saying. Okay? Because to me, it didn't make sense when I read it. So I'm a visual person. I need to understand it. So that was for the C. This is for the S. Okay, to me, I've taken the teeth out of this problem now. So this is valence. So A, based on the student's hypothesis, what would be the formula of the compound that forms between chlorine and fluorine? So how many valence electrons does chlorine have? It appears to me that it's 7. Right? So my formula is 8 minus 7. It'd be 1, wouldn't it? So I'm just going to mimic this. It looks like I put the compound first and then F. So it should be ClF. And you get 1 point for that. Right? And whoa, what? Because that'd be 8 minus 7 equals 1. And that would be the number of fluorines. This is the valence electrons. I'm just following what they told me to do. B, in an attempt to verify the hypothesis, the student researches the fluoride compounds of other halogens and finds the formula ClF3. Don't let that mess you up. Like, oh my gosh, it's supposed to be ClF3. It said that they were looking at other things. In the box below, draw a complete Lewis electron dot diagram for a molecule ClF3. Okay, this is not about geometry. It's about just making the right bonds. So I would make Cl with 3 Fs. And this is where, if you approach this the same way every time, you're going to come out ahead. Put the dots on everything that should have them to make an octet. That's my first step. Now I want to check, do I have enough? So you do need to look at the periodic table, and this should have 7, and this has 7 times 3. Where am I getting it? They're all halogens. It's group 17 or 7A. So that's 21 plus 7. I should have 28 valence electrons. How many do I have drawn right now? 8 times 3 is 24, plus 2 is 26. So I am short by 2. So where do I add them? On the center, right? Never on the outside. We only break octets in the middle. So that is something where I think we should all be able to do that. You just have to take a breath and go, hey, do I have enough dots? It's not about memorizing it. I don't have that stuff memorized. There's no need to, because I understand how to apply the idea of how many valence electrons I need. So if you ever need to add more, if you don't like how you did your first 2, you can always clean it up and kind of space them out a little bit more, but we're not drawing an actual shape. We're just drawing an overall Lewis structure. So 1 point is earned for the central atom, surrounded by 3 bonded pairs with F atoms and 2 non-bonding pairs of electrons. F atoms must have 3 non-bonding pairs. Each pair of electrons can be depicted as dots. So it's just 1 point. Final part of this problem. 2 possible geometric shapes for ClF3 molecule are trigonoplanar or T-shaped. The student does some research and learns that the molecule has a dipole moment. Talk about that. Which of the two shapes is consistent with that fact that the ClF3 molecule has a dipole moment? Justify your answer in terms of the bond polarity and molecular structure. It can be worded in 1,000 ways, but this is a really important question because it will always be asked. First, I expect, at least when we did this chapter, I would have expected you to tell me this is T-shaped already. Okay, there's 5 clouds, parent geometry is trigonal bipyramidal, and we would have done all sorts of fun stuff. You don't have to draw this necessarily, but this would have been, I mean, it's not asking about geometry necessarily. Oops, I'm doing too many. But we learned this a long time ago. That's what we would have done. We would put the 2 lone pairs where the 2 bonds are and all that stuff. This is the key. If it says dipole moment, I'd write this down on your sheet. That means it's polar immediately. Okay? So let's talk about that. Actually, you might want to draw this because trigonal planar looks like this. So I'm going overboard here. Dipoles point towards the atoms that are in the most upper right. So F's are always the best. So when you want to talk about something that's polar, I read this every year. It says, explain why it's polar. Explain why this has the polarity, greater polarity than that. You never say anything about the lone pairs. They don't care about it. It's not a reason. All you need to talk about is being symmetrical or asymmetrical, and then you need to talk about dipoles either canceling out or not canceling out. That's it. So the fact that it has a dipole moment, that's what that means, by the way. A dipole moment's a big arrow, like one arrow saying, hey, this is the negative end, that's the positive end. So which one is it? It's T-shaped. Because it is asymmetrical. And the dipoles do not cancel out. Whenever you're talking about polarity, either the dipoles cancel out or they don't. It's not because it has lone pairs. And that's it. So it could just say, explain why one's polar and one isn't. Trigonal planar, the dipoles cancel out. So there is no dipole moment. The other one, the dipoles do not cancel out. So there is a dipole. Oh, sorry, there's one more part. I thought that was done. Final part. In an attempt to resolve the existence of ClF3 molecule with the hypothesis stated above, the student researches the compounds that form between halogens and fluorine and assembles the following list. So this is what they make. Based on concepts of atomic structure and periodicity, so basically structures, how they bond, how many times they can bond, periodicity, meaning size of the atoms, ionization energy, electronegativity. Propose a modification to the student's previous hypothesis. What was their previous hypothesis? 8 minus the valence electrons, that's it. For the compounds that form between halogens and fluorine. All right, we'd have more time to look at this. These kinds of problems are hard. So what you have to basically do is fill this in, and as you go, you need to come up with some sort of an idea of how many F's bond to these halogens, okay? So for sake of us working on this, we'll just jump into this. This first one doesn't help you a lot, but as you move down, what do you notice about the number of F's? They are always odd, aren't they? I mean, I'm just making observations here. So I have odd number of fluorine atoms. And then what happens? What do you notice as you're moving down? What happens to the number of possibilities? And I'm just doing like literal observations that I'm noticing. Aren't I gaining a possibility for a formula every single time? So I'm gaining those based on what? What's happening? This is the periodicity part. What's happening to my halogens? They are getting bigger. So as the halogen gets bigger, I gain more possibilities, or I gain another formula. The atomic number of the central halogen atom increases, the number of F atoms increases. You could say that too. The number of different F atoms that I can have. You can even talk about the maximum number. It went from 2, and assume it's a larger number. Here you go 1, 3, 5, 1, 3, 5, 7. So I'm gaining more. So as the halogens increase in size, the number of fluorines increase. You don't see it. Some trend problems are tough. Making an observation or a rule, that's tough. It's not the norm. It's not a standard thing that we always have to do either. So, but that was only a point. So if you recognize it, great. If you didn't, it's not the end of the world. All right, we're moving on. You know, this is slightly fast-paced, but trying to kind of see how we're approaching atoms, elements, structures, and properties of matter. All right, a student places a mixture of plastic beads. So there's these two different plastic beads. Either we have polypropylene, which is we're going to call PP, or polyvinyl chloride, which is PVC. You might have heard that before. In a liter container, after stirring the contents of the beaker vigorously, the student observes that the beads of one type sink to the bottom and the other type float. So one sunk, the other was floating. And then here's the structures. A, given that the spacing between the chains are the same, the beads that sink are made of which polymer? Explain. So we're not talking about density. That's why they talked about space. So what is the goal? With any of this stuff, guys, you just got to find the difference. And what's the biggest difference you notice? This is what I see. This has CH3s versus this has CLs, right? Well, what things sink? Things that are more dense. Well, if it doesn't take up more space, that's what they're telling you, then the other part of density is mass. So this is a lot heavier than that, than CH3, right? So it would make sense that A, PVC sunk. And I would say because the chlorine is heavier, it has a greater mass than CH3. Cl has a greater mass than CH3. That's it. I didn't know that beforehand. I looked at the pictures and I said, well, okay, here's the difference. Well, Cl's heavier. That's the point. Okay, next part. PP is synthesized from propane, and PVC is synthesized from vinyl chloride. So we give you the two. The structures of the molecules are shown below. So now we have two new structures here. B, the boiling point of liquid propene, 226, they give you some numbers here, is lower than the boiling point of vinyl chloride. So this is 226. If you can't see it, write it next to it. Like if you're having a hard time reading it, sometimes numbers and phrases don't jump out. I mean, what's the harm of, okay, I'm going to write it down. I'm going to put it right next to that structure because I know I'm looking at a structure so I can understand this better. It says account for this difference in terms of the types and strengths of intermolecular forces. Okay, so what do we know? The stronger the IMF, the higher the boiling point. Everything is always higher except vapor pressure. The stronger the IMF, the stronger the anything except for vapor pressure. It's the only one. Vapor pressure, the weaker it is, the easier it is to leave. So this must have stronger IMFs, right? The vinyl chloride must have stronger IMFs. So all you truly have to say, this is my suggestion. You list what they have, and then you say which one is stronger or weaker, okay? And this should make sense that they probably both have dipoles and Londons. I mean, they're not symmetrical. That's not even. That's not even. So what I would say, in this case, both have dipole, and then they're always London, but it's not a bad thing to say. But you can talk about this in many ways. You could potentially say that the Cl has a greater electronegativity, causing a stronger dipole. Even if you went down the London force area, if for some reason, you know, they were quite equal, this is a much larger molecule, atom than the CH3, so it's more polarizable, we always use. But I would just say that the vinyl chloride has a stronger dipole due to the Cl versus the CH3. I'd be very specific. Okay? And if you feel like, well, I'm just kind of being generic in general, it doesn't have to be that mind-blowing. You're just showing that you understand what IMFs are. Listen to the final sentence. The intermolecular attraction are stronger in vinyl chloride, which results in having the higher boiling point. Right? This also does have a larger electron cloud, which causes it to have a stronger attractive force. Okay? So that's just one point. We only have one more part on this. We're doing okay. So you can kind of finish that one up. I know I didn't finish writing it, but I would have talked about that Cl is larger, and thus we have a stronger IMFs. I've already stated what they are. In a separate experiment, the student measures the enthalpies of combustion of propene in vinyl chloride. The student determines that the combustion of 2 moles of vinyl chloride releases 2,300 kilojoules of energy according to the equation below. Oh, shoot, they already said it right here. By the way, here it is. If you're wondering what all that wording is right here, there's 2 of these, 2 moles of my vinyl chloride releases, and then the release part is my negative. Right? Okay, C, using the table of standard enthalpies of formation. By the way, let's talk about that quick. That's what that means. Do you ever see that phrase? Standard enthalpy of formation. It's making each of these from its elements. Okay? Determine whether the combustion of 2 moles of propene, instead of 2 moles of the other one, releases more or less or the same amount of energy that 2 moles of the vinyl chloride, which is above. Justify your answer with a calculation. So I just got to do math. Okay, I'll help set it up. You can do the math on this. The balance equation for the combustion, and they give you, they tell you what it is. So here's 2 moles. So, okay, here's the trick. Are you doing products minus reactants, or are you breaking bonds, then making bonds? That's the trick on this. Well, these are standard. I would actually write it, if you didn't already, right here. To do bonds broken minus bonds formed, you'd have to see bond energies. Okay? That would be broken minus formed. This is the trick that students have to overcome. Are these bond energies? No. It doesn't say the word bond energy. These aren't actual bonds. These are actual compounds, right? A bond would be like CC, HC, C double bond C. Like, that's a bond energy. And that's a big difference. So this is products minus reactants. Okay? So all you need to do is, let's start here. So CO2, what I'm going to do, there's 6 of them, times negative 394, plus, so I've done that one. Water, I have 6 of those, times 2, negative 242. That's my products. Right? This is my CO2. I'm just writing this down for you just to visually see it. I put those in brackets. You add those up. It's the sum of the products minus the sum of the reactants. I have 2 I gotta find it. Sorry, 2 moles of my what is this? Vinyl chloride. And I have 9 moles of my oxygen. Oh, that's weird, it's 0. Well, we have learned that the enthalpy of formation of an element is 0 because it doesn't take any energy to make what's already made. It's already there. So now you need to add up the products, and then you need to subtract the sum of the reactants. In this case, it's nice that it's a 0. And you'd be amazed how you get this answer. You get 2 points, or the points for this. First one's the math. Okay, you get that down. But if you didn't say anything, most students, I imagine, that did this problem did not finish. They put the answer down and then they walked away. It asks, does it release more, less, or the same amount as the other thing? So I need to compare it to that number. So I don't know if anybody got it or if we're just not going to try. I don't know where we're at on all this, but this is what I got. And honestly, at some point, we should have put a unit. And I'm a little uncomfortable that I didn't. So it's asking which one releases more. This is negative 3858 versus negative 23. Which one releases more? Top or bottom? I'll make sure. This is releasing, but it's less number. It's releasing more. Remember, a negative with energy is just a direction. So I'm releasing more. So what I would have said is that the vinyl chloride releases more energy. And then you could say than the propene if you needed to. But that, you had to say it. You got another point for saying that it released more, believe it or not. And I think a lot of people probably moved on after they answered it. All right, we have two short ones to end. I did this on purpose because I knew it was going to get a little tight and we can kind of get that energy and moving forward. And I know we're just about at time, but this will be good. There's one thing that was missing on this next problem for you, I believe. If it's not this one, it's the next one. And I apologize. I will fill in the blank for you. And maybe not. Oh, you don't need to write it down. Is yours start right here? Is that true? Okay, so just take it in. Okay. You don't need to for surely write the top. If you want to write this little table, you definitely can. It might help you on that. So you could put Li and then radius 76 versus Na plus 102. But it says to explain. Now, understand this is already starting at B. So if you're like, where's A? A was totally unrelated to this big idea, and I didn't feel like it affected the rest of this problem enough. And I don't actually know what it was anymore. This is from 2 years ago. This is 2016 only. These are the actual tests, by the way. Like, this is what they were taking just recently. To explain why the change in H for the NaCl is different than that for LiCl, the student investigates factors that affect the enthalpy of solution and finds that the ionic radius and lattice enthalpy, which can be defined as the change of H associated with the separation of a solid crystal into gaseous ions, contribute to the process. The student consults references and collects the data shown in the table below. So again, you might just want to have that table written somewhere. Sorry, I cut that off. But you read that and go, I don't know what I'm doing. But yet, letter B, not that much here. Write the complete electron configuration for Na plus ion in the ground state. Don't let ground state confuse you. That means that we fill it in from the bottom. So I say 1s2. That's what we're doing. Okay? So it's Na plus. So what am I going for? How many electrons? So look at the periodic table. I have 11. So I am actually doing how many electrons? 10. I want to do 10 electrons. And this is, there's many ways to do this. You can understand and memorize where things are in blocks. Hey, that is the S block. That's the P block. I understand that. You might remember the order, but that's something that you have to review a little bit. So that's 1s2, 2s2, 2b6. That's it. So that's 1 point. Nothing more to that one. C, using principles of atomic structure, explain why the Na plus is larger than the Li plus. Okay, well, they're both plus, so the charge doesn't matter. So Li plus is here. I'm just drawing it on the periodic table, like where it's located. And they're right above and below each other, right? So it's saying, why is the Na plus larger than the Li plus? So what's happening when I go from Li to Na? I am gaining energy levels. Done. Can you talk about nuclear charge? No. The minute you talk about nuclear charge, you usually are talking about sucking in that atom or ion. So I would actually be very specific. Oh, ooh, hold on. I can't, this is good. I'm glad I made this mistake. Why can't I say Na plus has 3 energy levels? Because it doesn't anymore, right? It only has 2. But Li doesn't have 2 anymore, it only has 1. So what I would just say, I'm glad I made that mistake, Li has more energy levels than Li, causing it to have a larger radius. And I might have gone above and beyond writing that. Let me read what they wrote, just so you hear a difference. Valence electrons in La are in a higher principal energy level than the valence electrons in Li+. Electrons in higher principal energy levels on average are farther from the nucleus. So you could say that the outer electrons are further away because they're in a higher energy level. Something like that. Right. We're getting close. D. Which salt, Li or Na, LiCl or NaCl, has a greater lattice energy? Justify your answer. This is a great question to bring back up. Lattice energy is, they explained it up here, but let me just say it again. It's the strength that a salt has and how much energy it takes to break those ions apart after they're in this strong 3D structure. So, if you remember or not, it's a thing called Coulomb's law. And it's based on two ideas. You wouldn't have to write this, but if you did, you hammered it all the way home. Q is, and you could just remember the issues here. Q is charge, R is size. So, what is not at play in this one? Charge. Why? Li and Na are both +1. Cl is the same in each. So it's not about the charge. So this is about the size. And it's saying which has the greater lattice energy. So which one have a greater lattice energy? Bigger or smaller? Mathematically, I want the smaller one, right? Because if I lower this number down, that makes a larger relationship. So the larger lattice energy would be LiCl. And honestly, if you could remember this, you could say due to Coulomb's law, LiCl would have a larger lattice energy because Li is smaller than Na. If you're having problems with that, you could say Li's radius is smaller, so the bonds are closer to the nucleus, which makes it tighter or stronger fold or stronger bond. I'm sure they have a very long definition. LiCl, because Li ion is smaller than Na ion, the Coulombic attractions between ions in LiCl are stronger than in NaCl. The result is a greater lattice enthalpy. Two left on this one. Below is a representation of the portion of a crystal lattice of LiCl. Identify the ions in the representation by writing the appropriate formulas. I hope that you would know which one's which. And if you don't, then you just messed this up. First off, when you lose an electron, then that means there's less, you drop an energy level. Like if it's Li plus, you just dropped an energy level, so it shrunk. When you gain an electron, you're just getting bigger. But they're on different energy levels. So I hope that it would look like, I mean, Cl is lower on the table. So that's the bigger one. I know you're like, well, what am I doing? You're just making sure that you're saying Li is the smaller one and Cl is the bigger one. Amazingly enough, that's the question there. So that's what you had to do there. And then last part. F, the lattice enthalpy of LiCl is positive, indicating that it takes energy to break the ions apart. However, the dissolution, the dissolving of LiCl in water is exothermic. Identify all particle interactions that contribute significantly to the dissolution process, being exothermic. For each interaction, include the particles that interact and the specific type of intermolecular force between the particles. This sounds a lot harder than it needs to be. This is what you think about. It's talking about when it dissolves, okay? Let me make this real simple for you. It breaks up into that. What is it dissolving in? Water. So there has to be some sort of attractive force to surround that. Okay? So these are ions. And you could call them hydrogen bonds or dipoles or whatever you want. But there's a dipole here because it's polar. So literally, I know you don't probably remember this completely. I would say there's interaction, it's a good way to use the words, interaction between the Li positive and the Cl negative ions and water. That interaction is an ion dipole interaction. One of them, ions are just pure charge. A compound usually brings a dipole. They're very different. Well, these have charges. Yeah, but these are partial charges. So when you look back, if you look back at your IMF sheet, we had simply H bonds, dipoles, and London, but then underneath we had modified ones like a thing called an ion dipole. So you may or may not have gotten to that part, but 1 point is earned for identifying the particles that are interacting. So you're interacting with the Li in the water and the Cl in the water. So if you just said that the Li is interacting with water and the Cl minus is interacting with water, that's a point. And then if you recognize that, well, this is an ion and that's a dipole or a hydrogen bond, although this won't be a hydrogen bond. Please understand that. Hydrogen bond has to be between, like it had to be another water molecule. This is big. This is an H bond. This, because it's just positive, that and a negative end, this is floating around by itself as a dipole, so that's why it's attracted to that. So this is not attracted to hydrogen bond. Water is attracted to itself with hydrogen bond. All right. Shortest problem to end, and then we're done. Let's say you didn't understand anything, and we're still going through this stuff. You should be able to answer this. This is from just last year. And I do not think this one is as tricky as it sounds. It says a student investigates various dyes using paper chromatography. The student has samples of 3 pure dyes. So there they are. The liquid hasn't gone up yet, okay? And then they have an unknown dye. The student prepares a chromatography chamber shown above on the left by putting a drop on each dye at the indicated position on the chromatography paper. A polar material, by the way. Paper is always polar. And standing the paper in a non-polar solvent. So they told you this. I'd underline that. That's important. The developed afterwards, it went up and the liquid brought it all up. Are shown on the right. A. Which dye is the least polar? What did we learn about this? The dye itself is always, the longer it stays in, the more attracted you are to the solution. Okay? So we talked about this before. If I have 2 things like this, and this was polar, and this was non-polar, and you had 2 dots on each one, okay? Up here, the solution, if this was solution, the furthest dot here would be polar. Here, the furthest dot here would be non-polar, because it's most attracted, it stays in the liquid the longest. So if it's opposite, it's not attracted to the liquid, so it's not going to stay in the liquid as long, okay? So it already told you it's non-polar. So A, which dye is the least polar? Which one do you think? C, A, or B? So least polar, meaning potentially non-polar or least polar. Well, the solution is non-polar. So the answer would be, it's going to be C or B. Which one? Least polar means that it's going to be closest to non-polar, and what? The solution's non-polar. So the longer it stays in there, the more it's like the solution. So the answer should be C. Because the solution is non-polar, the dye that's the least polar will stay in there the longest because it's the most attracted to the solvent. 1 point is earned for the correct choice. 1 point is earned for the correct description. I just said it. The solution, the dye that stays in the longest or goes the furthest is the most attracted to the solution. Solution's non-polar. That dye would be the least polar. B is about as easy as it gets. Which dye is present in the unknown? Well, here's the unknown, and it's right next to these 3. Now, maybe you don't feel like it's that easy. I guess it could have been a little more obvious. I don't know. I mean, if you say C, you're way off. Oh, solvent front. So it only went this high, by the way. So they didn't pull as far. So you guys kind of got to match it up. And to me, that's the closest one. So A is present in the unknown. The unknown sample moves to a position that is midway between the origin and the solvent front. And so does dye A. So that's as far as the solvent went. It's about the same distance that it traveled. And you just had to recognize which one compares the most. The big thing I want you to get out of chromatography, again, is understanding that when you cause the solvent to go through the unknown, that unknown or that dye will stay in the solution as long as it's attracted to it. Okay? So a very polar compound will come out of solution because it's more attracted to the paper than the solution.